Hey everyone, today, Foundations 30 lesson today from section 1.4. We're going to talk about compound interest. We're going to work with the compound interest formulas, and we're going to talk today about present value, among some other things. So present value is in the title of the section, so that's kind of the main thing. Now, what are we talking about? Well, here's our original compound interest formula, and this is used to find future value. A, remember, is future value. Well, if we manipulate this formula a little bit, and I'll show you here what I mean. If we try and solve for present value, we try and isolate that, what we do is this. We divide off this portion, because p is multiplied by this up here. So if we divide that off, we divide it both sides, and we end up with p all by itself, because those cancel out. And so if p is all by itself, then what happens? Well, this is what's left over. And so the present value can be calculated by taking the future value. So if you know what kind of money you need in the future, you can go back and you can figure out what kind of money you need to put in now. If you're, let's say, putting something in a GIC or something that compounds, you can find out how much you need now. So that is this formula right here in the 3, and of course this is the focus of today. So there's your first formula, finding present value. Everything else is the same, I is the same, interest rate in decimal form per compounding period, n is the number of compounding periods, a future value. Now, this right here is another formula that we won't use all that often, but it's a way to compare investments. So if you have the same term or the same principal, and you can use the ratio of what the future value would be compared to the present value in determining kind of which would be better for you, right? So a divided by p, and it actually just equals 1 plus I to the power of n. So if we need that, you have a question about comparing investments, this is the formula you would use for that. The one formula that I do want to go over that's not on this list, okay, I'm going to show you how to solve for I, okay? So I'm just going to leave that section of the page up there a bit so we can see. Now, in order to solve for I, okay, let's say this is our original formula. Okay, here's the original future value formula. Now, if I want to solve for I, that means I want to get this guy all by itself. I got to get rid of this guy, I got to get rid of this guy, and I got to get rid of this guy, okay, to get this guy all by himself. So how are we going to do that? Well, mathematically, this is the order. This is sort of how you do that. Let's work from the farthest out first. So this p value, let's divide this off, both sides. So we get a over p on this side. And this is left with these p's cancel out. Okay? Alright, so now you're left with a over p. This is your a over p formula. Okay. Now, how do you get rid of n? Okay, this is, remember, to the power of n. So if you recall, the opposite operation of taking something to a power is taking the square root with this same number in the index. So for example, if this was 18, you'd have to take the 18th root of this value to get rid of this. So if you do that, this gets rid of that. Right? They cancel each other out, really. But what you do to one side, of course, you have to do to the other side. I know this looks really tricky, really confusing, but really it's not, okay? The opposite operation of taking an exponent is taking the root, okay, of that same number. So the nth root gets rid of the nth exponent. Now, we're almost done, right? We can get rid of these brackets because there's nothing outside. So what did I say we had to do? We had to get rid of this guy, and that's just a positive 1. So guess what? Let's just subtract the 1 from both sides. And so you end up with I all by itself here. That's gone. And we have the nth root of a over p. And then you have minus 1. Now, please make sure that this minus 1 is not underneath the radical sign here, okay? Not underneath here. It's separate, okay? So that's separate. When you do all this, you calculate this, then you subtract 1, okay? That's very, very important. Don't put that negative 1 underneath there, or else it's totally messed up, okay? So there's your formula for I, which would probably be a good idea. I'm going to put that with the rest of the, let's see, pink. So I equals the nth root of a over P minus 1. Okay, there you go. Same as that down there. All right, we good with that? Okay, I hope you understand that. These are the important formulas that we're going to use for this section. Okay. Now, I did do an example here, and I started one here for you, so let's finish this together. Okay. In this example, okay, we have Laura who's investing $15,500 in a education savings plan. Okay, she wants to give some money to her newborn baby when this newborn baby enters university right here. Okay, destined for university right there. This is a good mom putting some money away. Awesome, good for you. She wants it to grow to $50,000. That's what she wants to end up having when this kid's 18. That's awesome. Okay, and so really what we're trying to find is what? Oh, okay. Well, let's just take it a bit here. What interest rate compounded annually? Okay. So she's got 15. She wants it to grow to 50. We've got n right here. Okay. And we can fill everything in, and we can solve for I. So the one that's missing is I, right? What interest rate? That's the question. So we're going to solve for I. So we're going to use our interest rate formula right here, and we're going to plug in all the values that we have. So the present value, this is how much she has. Okay, she has 15,500. So let's put that in, right? Present value right here, 15,500. And the future value, she wants it to grow to 50. So that's A, 50,000 right there. And N, okay, well, let's read a little bit about N. 18 years, well, it's compounded annually. See that? Compounded annually. So N is going to be 18 then. 18 right there. So that's the 18th root. Now, don't get freaked out by this. Okay, I know it looks scary. It looks like, some upper level mathematics that, is going to cost $50,000 to learn how to do, but it's not. Okay, let's get rid of this stuff here. Quit that. Okay, so how do we do this? On this calculator, what you do is you have to do 18 first. Okay, you got to tell the calculator 18 here, and then you hit math, and you see this option number 5? That's how you do it on my calculator. Your calculator might be a little bit different. But then from there on now, you like to use brackets, but 50,000 divided by 15,500 end bracket. Okay, now let's just do this one first. Okay, so you get 1.06722. That's this value of this part. And then we're going to subtract 1. So minus 1. And we get this as a decimal, 0.067229. 0.067229. Now this looks an awful lot like the decimal form of a percent. And so the our percent, okay, is going to be 6.72%. That's the annual rate because this is compounded annually. So the decimal form of this is the decimal form of the annual percent. And if we look down, I don't know if I have it here or not. Oh, I don't have the answer here, but it's in the textbook, and this is correct. Okay, that is the correct answer. So you can pause now and take a look at that, and yeah, do that again if you want. That's kind of how you extract. Now I didn't do B. We didn't do B together, but I'm gonna because I want to do one more example for you. All right. So here's the first question in your assignment, and it says, first of all, I want to go over this. Predict which investment will require greater present value to be invested. Explain. So A says the future value of 10,000, so they want to end up with 10, invest at 5%, compounded monthly. Here's your key, 10 years. Everything in B is exactly the same. 10,000, 5%, 10 years, except for the compounding frequency. Okay? Now, what we know about compounding periods, okay, monthly, this is 12 times per year. Quarterly is 4 times per year. 4 times a year, right? 4 per year, 12 per year. So this one is going to get compounded more often. So check this out. Compounded monthly will grow more it will grow more and it will grow quickly. So less money is needed for A. Greater money will be needed for B. And so that's the reasoning right here, because it's compounded more often. So if we work out this problem down here, if we put all the values in for A and for B, okay, so again, future value, right? 5% compounded monthly, okay, so that's going to give us this for an I value, right? 0.05 divided by 12. That's what that's going to be right here. And over here, it's 0.05 divided by 4. That's the I value that goes in here. And so if we work those out and we find present value, we see that for A, we need $6,072, and for B, we need $6,084. So that, our prediction is confirmed from the first part, right? So we actually need more money to put in because this one grows quicker and grows more over the same time. Okay, and I just maybe one more thing I'd want to add here, because there's a question about solving for n, and what we have to do is we have to think back to the lesson about logarithms, because in order to get this n out of the exponent position, okay, we're going to have to use logarithms to bring it down. And so for this particular question here, fill in all these values. We want to get rid of this first by dividing it off, okay, both sides. Then you get this number right here when this is divided. So to get this n down here, we need to take the logarithm of both sides, okay, from previous chapter's work. And once we do that, the n can come down. Here it is, right here. And so we divide off this log of 1.136, and n equals this value right here. So on the calculator, it's just as simple as this: log of 164.109, bracket there, divided by log of 1.136, and n is 39.99999, which is 40. Okay, we can round that to 40, and so n equals 40, which is the number of compounding periods. Okay, so that's how you solve for